Hello students, welcome to MEMONEET. This is Aprajita, your chemistry SME, and we are back with our another lecture. So today the chapter that we are going to study is P block elements. So students, you know it is going to come in your next BPT. So basically this chapter has been divided in your class 11th and class 12th as well, right? So in P block elements, you know that we will study group 13 to group 18 elements. All right. So in this BPT, we have given you whole P block, means combined chapter of 11th and 12th as well. So you have to study both the chapters, okay? And we are here to help you out. So this is an important chapter. Basically, this is more of a theoretical chapter where you have to learn the things, okay? So in this chapter, main point is learning the things, understanding the concepts, okay? So let us start then. All right. So today I'll be covering group number 13, 14 and 15 in this lecture. So students, we all know that p block elements are the ones in which the last electron enters the outermost p orbital. So you know that we have 3 p orbitals, right? 3 p orbitals are there, px, py, pz, and the maximum number of electrons that can be accommodated in them are 6. Alright, so that is why there are 6 groups of p block elements starting from 13, 14, 15, 16, 17 and 18. And you know the first members are boron, carbon, nitrogen, oxygen, fluorine and helium. Okay, the valence shell electronic configuration is NS2 NP126. Okay, like NP1 for group 13, NP6 for group 18, except for helium. You know it's an exception. All right. So we will be starting with our group 13 elements. Before that, you see here that here we have written the general electronic configurations like NS2NP1 for group 13, NS2NP2 for group 14, NS2NP3, NP4, 5 and 6, and exception 1s2 for helium. Alright, first member of the groups are given boron, carbon, nitrogen, oxygen, fluorine, neon. Group oxidation state. Now how to find group oxidation state? Group oxidation state is actually equal to the number of valence electrons. Like in group 13 you see NS2NP1. So how many valence electrons are there? 3. 3 valence electrons. So the maximum oxidation state shown by this group is plus 3. Same goes for group 14, plus 4, group 15, plus 5, plus 6, plus 7, plus 8. Apart from it, they show other oxidation states as well, because these NS2 electrons, they are reluctant to participate in bonding, okay, or reluctant to participate in bond formation. This we call as inert pair effect. All right. So that is why they the higher elements, if I am talking about the higher group, like we move from left to right, so they will show 2 less oxidation state also, like plus 4, plus 2, plus 5, they will show plus 3 also, because with the that will be equal to the number of p electrons only. Okay, so these are the different oxidation states the elements will be showing. Now let us talk about the group 13, that is boron family. We will be mainly focusing on the important points, otherwise there is a lot to learn in the chapter. So you know that the elements are boron, aluminium, gallium, indium and thallium. These are the elements of boron family. You know boron is a non-metal, aluminium is a metal, okay, but there are some similarities to that of boron. Then gallium, indium, thallium, they are exclusively metal. We all know that when we are moving down the group, metallic character increases. Outer electronic configuration, NS2NP1, we all know. Now, if I am talking about the trends, so in the last chapter in periodicity, we have discussed it in detail. So here we will be just talking about the trend and whenever there is some exception. So on moving down the group, you know, one extra shell gets added from boron, aluminium, gallium. So what happens is the atomic size should increase. So the expected size should be boron, aluminium, gallium, indium and thallium. But you know students that this is not the right one. There is a change. The size of gallium is less than that of aluminium. Okay. Now why that happens? Because see, not only the outer electrons are affecting these things, the inner core electrons. Core electrons are responsible for various change in physical properties and chemical properties. If I am talking about gallium now, gallium comes after D block. So gallium may we have d electrons, and you know that the d electrons, they offer poor screening effect. Okay, so because of poor shielding effect of the additional 10 d electrons that are there in gallium, the nuclear effective nuclear charge will be more. So there will be increased nuclear charge in case of gallium. So that is why atomic radius of gallium is less than that of aluminium. So now this kind of questions will be asked in NEET. Like they will give you group 13 elements and they will ask you to arrange them in atomic size. So if you know the exception, then you can choose the right answer, otherwise it would be wrong if we go with the general trend. Okay. Now same goes for ionization enthalpy. Ionization enthalpy, you know ki when we are moving down the group, it should decrease, but it will not decrease smoothly because of the again the atomic size thing. There is a discontinuity between aluminium and gallium. Okay, then indium and thallium also. So generally it should decrease, but again due to the inability of D, because whenever D and F electrons will come in between, na, the trends will change. Okay, then if I am talking about electronegativity, first it decreases from boron to aluminium. Electronegativity, you know, it decreases, all right. Then it will increase. Okay, again why it is increasing? Because of the discrepancies in atomic size. Then if I am talking about the nature and other physical properties, boron is non-metallic in nature. It's hard and black colored solid. Okay, so due to strong crystalline lattice, it has high melting point. You should know this. It has unusually high melting point. Rest are soft metals, okay, with low melting point and high electrical conductivity. Okay, so you know that gallium also exists in liquid state during summers. Usually at room temperature it's a solid, but it can exist as liquid at higher temperatures. Okay, and density of the elements increases down the group from boron to thallium. All right, students, that is the thing. Now if I am talking about the chemical properties, so due to small, now you know that obviously the second group element will be having smaller size. So due to small size of boron, the sum of first three ionization enthalpy is very high. So that is why boron does not form plus 3 ions. Okay, for plus 3 ions banna, it's like difficult in the case of boron. So that is why it forms only covalent compounds. So boron will form covalent compounds. But you know, when you move from boron to aluminium, ionization enthalpies decreases. So aluminium can form Al3 plus ions. And you know it's a highly electropositive metal. Now when I am moving further downwards, because of poor shielding effect of D and F electrons, nuclear charge increases, alright, and when nuclear charge increases, it is holding Ns electrons tightly. What I told you na, ki S electrons do not participate in bonding, we call it as inert pair effect. That is happening in the higher elements, alright. So only p electron will be involved in bonding. So that is why gallium, indium, thallium, in addition to show the plus 3 state, they will show plus 1 state also, plus 1 oxidation, because s electrons will not participate in bonding. And the stability of plus 1 oxidation state will increase for heavier elements. You see here. Why? Because of the more shielding, like poor shielding of D and F electrons. So in thallium, plus 1 oxidation state is predominant. So if you are ever asked if thallium will form which kind of ion, it will not form thallium 3 plus, it will form thallium 1 plus, because it will be more stable or more predominant. Okay. And you know that in trivalent state, number of electrons around the central atom will be 6. Like if I am talking about BF3, covalent bonding will happen, but outermost shell will only have 6 electrons. So the molecule is electron deficient. So it has a tendency to accept a pair of electrons. So that's why they behave as Lewis acids. Like here you can see BCl3 and ammonia. Ammonia will donate its lone pair of electron. We have studied this in coordinate bonding. Okay, so you will get this complex, and AlCl3 also exists as a dimer because of this thing. Okay, next up, so now if we talk about the chemical properties, so here you can see boron is unreactive in crystalline form. All right, aluminium is a highly reactive metal. It forms a thin oxide layer on the surface. Once that oxide layer gets formed on the aluminium, it will prevent, it acts as a barrier. So it will prevent further oxidation of aluminium. Okay, so here you can see कि amorphous boron and aluminium will form B2O3 and Al2O3, and with dinitrogen they will form nitrides. Alright, so here E is the element. So boron but you should know the nature of the oxides because questions are asked on the nature of oxide. So boron trioxide will be acidic. Okay, it will react with the metallic oxides forming metal borates. Aluminium and gallium oxides are amphoteric. You should know that this is an amphoteric oxide, means it can react with both acids and base. And for indium and thallium, they are basic. Because when we are moving, now how will you remember? When you are moving down the group, metallic character increases, right? And you know that metallic oxides, they are basic in nature. So try to remember that ki the lower element oxides, they will be basic in the properties. Then reactivity towards halogens. So they will be reacting with halogens to form trihalides, all right, except thallium will not react. Then if I am talking about acids and alkalis, boron does not react with acids and alkalis at even at moderate temperature. Aluminium जो है, it will get dissolved in acid and alkali as well. So it's an amphoteric metal. Okay, so with acid, it will liberate hydrogen gas. You know metal plus acids give hydrogen gas. But if I am reacting aluminium with nitric acid, it will not react because it will form a protective oxide layer on the surface of aluminium. And with alkali also, it will form sodium tetrahydroxoaluminate, which is a compound, complex compound, and hydrogen gas will be evolved. So see, I told you, you have to remember these things. All right. So this is more of a remembering chapter. Now let's talk about the compounds of boron. So on these also sometimes questions are asked, like borax. Borax is an important compound with the formula Na2B4O7.10H2O. All right. And the correct formula will be this. So borax will dissolve in water to form alkaline solution. It forms orthoboric acid H3BO3. Okay, so you might have heard of a test called borax bead test. So this borax is also used in that borax bead test in the qualitative analysis. Okay, so for uh, you can say for the analysis of transition metals, we get different colored beads. Okay, with this borax. So that's why it is easy for us to find out which ion it is. All right. Like see borax when it is heated in a Bunsen burner with cobalt oxide. So a blue colored bead will be formed. So that will tell us ki it's that compound is having cobalt ion in it, right? Then if I'm talking about orthoboric acid, so you should know its structure here. H3BO3, white crystalline solid with soapy touch. It's sparingly soluble in water but highly soluble in hot water. Now the thing is how it's prepared by the aqueous acidifying an aqueous solution of borax. Okay, borax se it is formed. Alright, and it is also formed by the hydrolysis of boron halides, hydrides as well. You can see that BO3 units are present which are joined by hydrogen bonds. So this is an hydrogen bond in this case. Okay, you can see the structure. These dotted ones are showing you the hydrogen bonding. Okay, it's a weak monobasic acid. All right, monobasic means its basicity is 1. All right, so its basicity will be 1. It's not a protonic acid, but it's actually a Lewis acid. Why? It will accept the electrons. Okay, so try to remember this. Next important compound is diborane. So students, on diborane, usually the question is asked on its structure. Okay, so boron, you know, simplest boron hydride known as diborane. It is now how it is prepared. You should know the preparation also, by treating boron trifluoride with lithium aluminium hydride in diethyl ether. Okay, and in laboratory preparation we are heating sodium borohydride, which is NaBH4, with iodine, so we will be getting diborane. And on industrial scale it is prepared by the reaction of BF3 with sodium hydride. So 3 methods are given: lab preparation, general preparation, and industrial method as well. It's actually a highly toxic gas. Okay, it catches fire on exposure to air. It burns in oxygen to forgive enormous. Can you see the delta H value? It's so highly negative. So large amount of energy is released. Okay. So these boranes, they get hydrolyzed with water to form boric acid. So these reactions you should know. Ki when borane reacts with water, what reaction happens? Okay. All right. So it undergoes cleavage reaction with Lewis base to form borane adducts. You can see here with ammonia it will form a complex, and on further heating it gives you borazine, which is known as inorganic benzene, B3N3H6. Okay, this you should know. So alternate BH and NH groups होते हैं उसमें like this. You know na benzene. So this is borazine. Like you can draw also. NH, NH, BH. Okay, so alternate groups are present. All right. Now, if we see the structure of diborane, so it has banana bonds in it. Okay, bridging hydrogen atoms होते हैं. Now you can see here. Let me show you. Yeah. So see, you know that B2H6, but boron has only 6 electrons. Oh, sorry, 3 electrons. Okay, if boron is having 3 electrons, okay, 2s2, 2p1, right? So how it is going to form 4 bonds? All right. So what happens is 2 bonds, they are formed with hydrogen, means 2 electrons यहाँ पर share हो जाते हैं, and same this boron will do. Now these have one electron each, and hydrogen has 1. So in this case 1 electron here will be shared with the hydrogen and 1 here will be shared. So this type of bonding is called bridge bonding or banana bonding. So there are 3 atoms, but the electrons involved in these bonding are 2. So we will call it as a 3-center 2 electron bond. Okay, these are 2 center 2 electron only, दो atoms and दो ही electrons shared हैं. We all know single bond में 2 electrons are shared. So this is a 2 center 2 electron bond. Okay, but in this case bridge bonding 3 atoms and 2 electrons, right? So you should know here that there are 4 2 center 2 electron bonds, and there are 2 3 center 2 electron bonds in the structure of diborane. Okay, this was the important thing you should know. Now let us talk about group 14 family, that is our carbon family. The first member is carbon. All right. So let us talk about it. So we have carbon, silicon, germanium, tin, and lead. So valence shell configuration is ns2np2, but inner core electronic configuration, you know, that is going to differ. So again, if I am moving downwards, there will be an increase in covalent radius. We have studied what are covalent ionic radii, right, in the last chapter. So increase from carbon to silicon. Then of course the trend should be that it should increase only. Then after from silicon to lead, a small increase is observed. Increase is happening, but a small increase. Why? Because again, completely filled D and F orbitals are present in heavier member. They show poor shielding effect, so more nuclear charge, although the size is increasing, but a very in a little amount. Okay, so first ionization enthalpy of group 14 members are higher than that of 13. You know, when we move left to right, ionization enthalpy will increase. Okay, so influence of inner core electrons also we can see, and down the group generally ionization enthalpy decreases. Okay, so small decrease happens from silicon to germanium to tin, but from tin to lead there will be a slight increase. Now again, that is an anomalous behavior. Again, why it is happening from tin to lead? Because of poor shielding effect of D and F orbitals. Okay, and then due to small size, the elements are more electronegative than group 13 elements, and electronegativity value for silicon to lead are almost the same. So all the group 14 elements are solids. Carbon and silicon, they are non-metals. Germanium, you know, it's a metalloid. And tin and lead are soft metals with low melting point. So what we are seeing is that when we are moving down the group, metallic character is increasing, and this is happening in every group. Okay. And melting and boiling points of group 14 elements are higher than that of group 13 elements. Now let's talk about chemical properties. So obviously they will be showing the +4 oxidation state. Apart from +4 oxidation state, NS2NP6 is there, na? NS2NP2. So due to inert pair effect, they can also show +2 oxidation state, but for higher elements. Okay. Carbon also shows negative oxidation states, you know that, all right. Okay, and generally these compounds are covalent in nature. In heavier members, you know, +2 oxidation state tendency will increase from germanium to tin to lead because of inert pair effect. Okay, again same thing we are telling in every group, because of the inability of ns2 electrons to participate in bonding. All right. Carbon and silicon mostly will show +4 oxidation state. Germanium forms stable compounds in +4 oxidation state and few in +2. Whereas tin and lead, you know, tin and lead, they will show +2 and +4 oxidation state. You know, like we have stannous chloride, stannic chloride, like PbCl2, PbCl4. So they will show they will show +2 as well as +4 oxidation state also. Okay, and you know the number of electrons around central atom are 8. Okay, so they are not electron acceptor or electron donor. Okay, and carbon cannot exist like exceed its valency more than 4 because of the presence of d orbitals in them, and due to this their halides undergo hydrolysis. And see, carbon cannot do that, but other elements can increase their covalency because of presence of d orbital. Like here you can see SiF6, GCl6. So here the hybridization is sp3d2. So d orbitals are also participating in the bonding. Then if I talk about reactivity, so two kind of oxides are formed, MO and MO2. Okay, like similarly carbon forms na carbon monoxide, carbon dioxide. So dioxides are acidic, uh, carbon dioxide, silicon dioxide and germanium dioxide. I told you when you are moving down the group, the basic nature of oxides will increase. Okay, and tin and lead oxide are amphoteric. Keep that in mind. Now towards water, carbon, silicon and germanium, they'll not be affected by water. Tin decomposes steam to form dioxide. In the presence of steam, it will form dioxide. Lead is also unaffected by water because of a protective film formation. Again, in the case of halogens, I told you they will form MX2 and MX4. Mostly MX4 compounds जो हैं, they are covalent in nature. Okay. So here the central metal atom, like you have CCl4, so carbon has undergone sp3 hybridization in this case. Now we have understood all these terms, right? sp3 and all of that. So exceptions are SN4 and PbF4. So these are ionic in nature. Okay, PbI4 does not exist because PbI bond does not release enough energy to unpair the 6s2 electrons. Okay. So if I am talking about heavier members, I told you from germanium to lead, they can also form mx2, like pbx2, okay, is more stable than pbx4. All right. So keep that in mind. So this all depends on the oxidation state. Now we know there are different allotropes of carbon. So diamond is there, in which each carbon undergoes sp3 hybridization. It has a tetrahedral structure. Okay. Three-dimensional tetrahedral structure, because of which it is very hard. Okay. Carbon-carbon bond length is given 154 picometer. So a rigid three-dimensional network is formed. All right, and that is why diamond is very hard. So you should know about its structure, the hybridization, okay, and the uses. Next, if I am talking about graphite, so graphite, you know, it is slippery because it has a layered structure. All right, and you can see here the hybridization of each carbon atom will be sp2 and hexagonal rings are formed. Okay, and each, so these layers, they can slip on each other, they can move on each other. That is why we can say that it is having a slippery nature, or it is soft and brittle as well. Okay, so if sp2 hybridization is there, so only 3 electrons are involved in bonding. 1 electron is a free electron. Okay, so these free electrons correspond to the good conduction of this graphite. So graphite is a good conductor of electricity. So because these electrons are moving, so that's why graphite is a good conductor of electricity. It cleaves easily and soft and slippery. Now let's talk about fullerenes. So they are made by heating of graphite in an electric arc in the presence of inert gases. So we have Cn number of molecules, like C60 is there, C70 is there, all right, but up to 350 can also go. So they are actually cage like molecules, like you can see C60, this is C60, which is having the shape of a soccer ball and called Buckminster fullerene. So 26 membered rings are there. Okay, means 20 hexagons are there and 12 pentagons are there. So hexagons and pentagons are there. So all the carbon atoms here undergo sp2 hybridization. These are important things that you should know. Okay. So now let us talk about group 15 elements: nitrogen, phosphorus, arsenic, antimony, all right, bismuth, and moscovium. So as we go down the group, you know that there is a shift from non-metallic to metallic character. Okay, non-metals and metalloids, then metal. Nitrogen and phosphorus are non-metals. Arsenic is your antimony, and arsenic are metalloids. Bismuth and moscovium are metals. Configuration: Ns2 Np3. S, you can see orbital are completely filled and p orbital are half filled, so their electronic configuration is extra stable. This is also we have studied. So if I am talking about radius, it increases down the group. From nitrogen to phosphorus, obviously it increase. From arsenic to bismuth, only a small increase. Why? We have already discussed, because of D and F electrons. Ionization enthalpy will also decrease down the group because of increase in atomic size. But you should know this, we have studied in the trend also, ki because of extra stable configuration, half filled p orbitals, ionization enthalpy of group 15 elements, it is actually much greater than that of group 14, and even it is greater than that of group 16 elements. That is what we should know. Electronegativity value generally decreases down the group with increasing atomic size. Okay, and all the elements are polyatomic. Nitrogen, like it exists as dinitrogen, it's a gas, while other elements are your solids, like phosphorus exists as P4. All right, so they are polyatomic elements in this case. All right. Now if I am talking about the oxidation state, so common oxidation state, since there are 5 electrons in the outermost shell na, so they can gain 3 electrons easily. So that is why means they can form anion. So -3 oxidation state can be there, +3 can be there by loss of these electrons, and +5 can also be there. If they are gaining electrons means non-metallic reactors, so nitrogen and phosphorus are non-metals, they can do. But once we are moving down the group, the stability of this or the tendency of the elements to show this -3 oxidation state decreases. Why? Because size increases and metallic character increases. So bismuth hardly forms any compound in -3 state, and the stability of +5 state also decreases. Okay. And +3 oxidation state stability will increase again because of the inert pair effect. So nitrogen exhibits +5 oxidation state, +1, +2, +4 as well. You know that with your oxygen it forms different types of oxides. Okay. Now nitrogen does not form any compounds in +5 oxidation state with halogens because nitrogen does not have d orbitals. Okay, phosphorus shows +1, +4 oxidation states. So this is general trend that different types of oxidation states are there. Okay, so nitrogen can actually show a maximum covalency of +4 only because there are no vacant d orbitals. All right. So other elements can expand their octet, but nitrogen cannot do that because of the absence of d orbitals, vacant d orbitals. So now let's discuss some anomalous behavior of nitrogen. So nitrogen differs from rest of the members because of small size, high electronegativity, high ionization enthalpy, and main importantly, non-availability of d orbitals. So nitrogen also has this ability to form p-pi multiple bonds. Okay, you know nitrogen has this triple bond in it. Okay, not just with itself, it can form these p-pi triple double multiple bonds with elements of small size and high electronegativity like carbon, oxygen. Okay, heavier elements of this group do not form these p-pi multiple bonds. Why? Because their atomic orbitals are large and diffuse, so they cannot have this effective overlapping of p orbitals, so pi bond will not be formed. So we know nitrogen exists as a diatomic molecule with a triple bond. Okay, and bond enthalpy is very high, 941 kilojoule per mole. So that is why it's a very stable gas. Okay. So on the contrary, phosphorus, arsenic, antimony, they will form single bonds. And bismuth forms metallic bonds in elemental state. Now you know that nitrogen single bond will be weaker than phosphorus bond because of high interelectronic repulsion of non-bonding electrons. Okay. So that is why nitrogen does not show this catenation tendency. Okay. Nitrogen cannot form d-pi p-pi bonds, you know, because it is not having vacant d orbitals. Alright. So keep that in mind. So if I am talking about their reactivity towards hydrogen, so they will form hydrides of type EH3. Now यहाँ पे you should know about the basicity. Okay. So hydrides, you know, stability of hydrides decreases from NH3 to BiH3. Now why this stability decreases? That is the question. Because the size increases, size of atom increases, so the bonding between the metal atom or the element and the hydrogen is not that strong. That is why as we move from nitrogen to bismuth, the stability decreases. Okay, and when the stability of the hydrides decreases, the reducing character of the hydrides increases. Okay, so you can say ammonia is a mild reducing agent, but BiH3 is the strongest reducing agent. Now you should know about the basicity also. So basicity, you know that nitrogen has a lone pair of electron. Okay, so will phosphorus will be having. But what happens is that phosphorus atom is bigger in size. So because of its big size, these bonding electrons, they move away. Okay, and moreover, this lone pair in this case is concentrated on a small atom and easily available for donation. But in the case of phosphorus, bond angle भी इसमें question आ जाता है. Okay, so in that case, phosphorus में the lone pair is available on a much bigger atom. So lone pair is easily available for donation in ammonia. So that is why when we are moving downwards, so the basicity decreases. Okay, and bond angle भी nitrogen ammonia में ज़्यादा होगा because bond pair goes away in the case of phosphorus and there is less repulsion, so the bond angle decreases. Okay, reactivity towards oxygen, so they can form two types of oxides, E2O3 and E2O5. Okay, similarly EX3 and EX5 types of halides are also formed. Nitrogen will not form pentahalide because again of the non-availability of d electrons in the valence shell, d orbitals. Okay, and pentahalides are more covalent than the trihalides. Okay, because the element, if it is in first +5 oxidation state, so you know that according to Fajan's rules, if the element is in +5 oxidation state rather than +3, so it will have more polarizing power. Okay, more polarizing power, so the covalent character will be more. All right, small size, high charge, more polarizing power. Okay, reactivity towards metal, so they can form nitrides in this case, like calcium nitride, calcium phosphide, and so these are the compounds that are formed. So you should know about the oxides of nitrogen. In this case, N2O is dinitrogen oxide. So here the oxidation state of nitrogen is 1. So you should know the oxidation states. In nitric oxide, this is also called nitric oxide, NO. Oxidation state is +2. N2O3 +3. NO2 means nitrogen dioxide, it's +4. Dinitrogen tetroxide again +4. Dinitrogen pentoxide, it is +5. Okay, and you should know their resonance structures as well. Just a minute. Okay, all right. Now, in another important topic of this is oxoacids of phosphorus, because phosphorus forms different acids. H3PO2 is hypophosphoric acid or hypophosphoric acid, then H3PO3. So here you should know the oxidation state of these acids. Apart from the oxidation state, these are the structures. So what happens is that in case of phosphorus, there is a double bond with oxygen, then OH, OH and OH. So this is H3PO4 orthophosphoric acid. These hydrogens are ionizable. Okay, if these hydrogens are ionizable, so here the basicity would be 3. Okay, let's say if I am talking about H3PO3. So do you think this pH would be ionizable? This pH is not ionizable. Only the hydrogens attached with oxygen are ionizable. So here the basicity would be 2. Okay, here the basicity is 1, hypophosphorus acid. So similarly we have other acids like pyrophosphoric acid, polymetaphosphoric acid. So we should know a little bit about their structures and the basicities. Okay, so I have covered the important topics of group 13, 14 and 15 elements. So try to revise all these topics and learn about them. In the next video lecture, we'll be talking about the other group elements. Okay, and if you are having any doubts, you can ask us in the comment section below. Alright students, so take care everyone. Thank you so much. Bye bye.